Lithium is the new white gold, and the world is racing to secure it before someone else does. Entire industries now hinge on a metal that, until very recently, barely registered outside chemistry labs and niche electronics. Electric vehicles, grid-scale batteries, renewable energy storage, all of it collapses without lithium. And while governments talk about supply chains and energy independence, the real story is unfolding quietly in the rocks beneath Australia. In the Pilbara of Western Australia, in a stretch of country that looks no different from 1,000 others, a forgotten mineral field has suddenly re-emerged to global spotlight. Not because it was newly discovered, but because the world finally caught up to what it contained. The place is called Tabba Tabba, and it may be one of the clearest examples of how the next resource rush won't come from new ground, but from old ground seen through new eyes. Tabba Tabba wasn't supposed to be a lithium story. For decades, it was only known as a tantalum field, worked intermittently in a time when tantalum mattered more than battery metals. Early drilling cut straight through lithium-bearing rock, logged it, and moved on. There was no reason to stop. Lithium wasn't strategic, it wasn't scarce, it wasn't valuable enough to shape decisions. So it stayed in the ground, waiting. That waiting ended when modern exploration returned and asked a different question. Instead of where is the tantalum, the focus shifted to what else is here. Drill rigs began intersecting thick, continuous bodies of lithium-rich pegmatite, not narrow veins, not isolated pods, but stacked sheets of mineralized rock extending for kilometers. When the numbers came back, they forced a rethink. The current resource at Tabba Tabba stands at roughly 74 million tons of ore, grading about 1% lithium oxide. That number alone doesn't mean much until you translate it into scale. That amount of lithium oxide equates to hundreds of thousands of tons of contained lithium metal, enough to underpin decades of battery production. Converted into spodumene concentrate and priced at recent market levels, the lithium sitting in the ground at Tabba Tabba carries an in-situ value measured not in millions, but in tens of billions of dollars. In Australian dollar terms, even conservative assumptions push the value north of $40 billion before mining losses, processing costs, or capital expenditure are considered. It's not revenue, and it's not profit, but it is an unmistakable signal. This is no longer a speculative occurrence. It is a globally significant lithium endowment sitting in a country already critical to battery supply chains. What makes Tabba Tabba unsettling is not just its size, but how long it was overlooked. The lithium was always there. The geology never changed, only demand did. And that shift in demand is now reshaping how entire regions are re-examined, remapped, and revalued. To understand why Tabba Tabba exists at all, you have to step back hundreds of millions of years to a time when the Pilbara was not a stable, arid plateau, but a tectonically active crust riddled with intrusions. Deep beneath the surface, granitic magmas were forming and slowly evolving. As these magmas cooled, early minerals crystallized and dropped out, stripping the melt of common elements like iron, magnesium, and calcium. What remained was a residual melt enriched in elements that don't easily fit into normal mineral structures: lithium, tantalum, cesium, tin, boron. These elements became increasingly concentrated as crystallization progressed, until the melt was chemically extreme and physically mobile. When pressure built, that final melt was injected upward into fractures, faults, and structural weaknesses in the crust. The result was pegmatites, coarse-grained igneous bodies that crystallize slowly enough to grow large mineral crystals and trap extraordinary concentrations of rare elements. At Tabba Tabba, those pegmatites formed as part of a lithium, cesium, tantalum system, the same family of deposits that host the world's most important hard rock lithium mines. But pegmatites don't intrude randomly, they follow structure, and at Tabba Tabba, structure was everything. The deposit sits within the Tabba Tabba greenstone belt, a narrow slice of deformed volcanic and sedimentary rocks, bounded and dissected by shear zones. One of these, the Tabba Tabba shear zone, acted as a crustal pathway, guiding pegmatitic melts into favourable positions. Complicating this further is the presence of a thick dolerite seal intruded into metasedimentary rocks. This dolerite acted both as a mechanical barrier and a chemical contrast, forcing pegmatite emplacement along its margins. The result is a stacked geometry, multiple lithium-bearing pegmatites layered one above another, dipping gently, continuous over long distances, and open at depth. This stacked architecture is critical. It means the deposit isn't a single lucky intercept, but a system. One body led to another, then another, each discovery reinforcing the idea that Tabba Tabba isn't just mineralized, it's organized. The pegmatites have names now: Leia, Luke, and others, but they are expressions of the same underlying process. The Star Wars names at Tabba Tabba weren't chosen for novelty, but because each pegmatite earned its identity through discovery. Leia was the first to reveal the system's true scale, intersected over extraordinary widths at constant lithium grades, forming a large, continuous body that remains open along strike and at depth. That discovery set a geological expectation, and Luke confirmed it. Luke was found not by chance, but by prediction, validating a vertically stacked architecture where multiple lithium-bearing pegmatites repeat through the system. As drilling expanded outward and downward, additional bodies named Chewie, Han, and Hut emerged, each reinforcing the same chemistry, geometry, and continuity. Together they show that Tabba Tabba is not a single lithium occurrence, but a coherent district-scale system, where discovery is no longer about finding lithium, but about mapping how much of it the geology has already concentrated. At Tabba Tabba, lithium recovery follows a deliberately conservative, industry-proven processing route designed to turn coarse pegmatite into battery-grade concentrate with minimal technical risk. Ore from the open pit is delivered as run-of-mine material and passed through 3 stages of crushing to progressively reduce it in size before screening splits the stream into oversized and undersized fractions. Oversized material is returned for further crushing, while the correctly sized material feeds a ball mill, where grinding liberates spodumene crystals from quartz, feldspar, and mica. From there, the slurry moves into a separation circuit where desliming removes ultrafine clays, magnetic separation strips out iron-rich minerals, and 3-stage flotation selectively concentrates spodumene using controlled surface chemistry. The resulting concentrate is thickened, filtered, and dewatered into a high-grade spodumene product, while tailings are thickened and pumped to storage. It's a flowsheet refined over decades of hard rock lithium mining, not experimental, not speculative, and it exists for one reason: to reliably extract lithium locked into ancient pegmatites and convert it into globally traded energy commodity. Modern discovery at Tabba Tabba wasn't driven by intuition or bush luck, it was driven by resolution. High-resolution drone imagery picked up subtle surface expressions of pegmatites that older surveys missed. Targeted drilling tested those expressions, and when the first lithium assays returned, the exploration strategy pivoted hard. What followed was rapid expansion drilling that turned a curiosity into a resource. In September of 2023, the lithium discovery was formally announced, and from there the story accelerated. Additional pegmatites were identified, including blind discoveries concealed beneath shallow cover. Metallurgical testing confirmed spodumene as the dominant lithium mineral, capable of producing saleable concentrate. A pre-feasibility study followed, demonstrating a pathway toward development. Today, Tabba Tabba sits in an uncomfortable but powerful position. Mining leases are in place, studies are advancing toward definitive feasibility. Infrastructure exists nearby, and the Pilbara is already one of the most mining-ready regions on Earth. The only real uncertainty is timing, dictated not by geology, but by lithium prices, capital markets, and how quickly the energy transition unfolds. This is what the next white gold rush actually looks like. It isn't prospectors stumbling over new outcrops. It's companies revisiting old ground, armed with new questions and new tools. It's the realization that many of the world's future supply constraints aren't hidden in unexplored wilderness, but buried in datasets written off decades ago. Tabba Tabba also reveals something deeper about Australia's position in the global energy transition. The country already dominates hard rock lithium production, not by accident, but because its geology specialises in exactly this kind of deposit. Ancient cratons, long-lived tectonic stability, repeated magmatic events, these are the ingredients that concentrate lithium into a mineable form. As demand grows and competition tightens, the importance of deposits like Tabba Tabba will only increase, not because they are flashy, but because they are real. The lithium is there, the rock chemistry is understood, the processing pathways are known. The only thing left is to decide when the world is ready to extract it. And that may be the most important takeaway of all. The next resource rush isn't about discovery anymore, it's about recognition. Lithium didn't suddenly become rare, it became necessary, and in places like Tabba Tabba, Australia is discovering that the future was sitting quietly in the ground all along. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.